Hi friends, here I am going to present session 6 of the paper 7 analysis 2 and algebra 4 of 6 some mathematics. The topic is analytic function. So it is not came in real function. So in real functions we cannot define analytic function. So only in case of complex function we define analytic function. So let us see the definition of analytic function. So what is an analytic function? A function f of z of a complex variable z is said to be analytic at a point z naught if it is differentiable at z naught and also at every point of some neighborhood of z naught. See here, the function f of z is said to be analytic if it is differentiable not only at z naught and also in the every point of some neighborhood of z naught. So neighborhood means it is around z naught, the points around z naught. So less than, greater than. So all the values lies around z naught are called the neighborhood of z naught. So analytic means it is differentiable not only at z naught. So in case of real numbers, in the case of real functions, we define only differentiability, not the analytic condition. So here in complex functions, we can define analytic function as the differentiability at z naught and also in the neighborhood of z naught. The function f of z is analytic in a domain D if it is differentiable at every point in D. So this analytic function is also called as regular function or holomorphic function. So to verify whether the given function is analytic or not, we have a necessary and sufficient condition. So that condition is known as Cauchy-Riemann equations. So let us see what is Cauchy-Riemann equations. It is a necessary condition for the function f of z is equal to u plus iv to be analytic in a domain D is u and v satisfy the equations, that is the partial derivatives dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. Because u and v are functions of x and y, so there the derivatives are partial derivatives. So these equations are called Cauchy-Riemann equations or simply CR equations. So let us see the necessary condition for analytic function. So in terms of theorem, if f of z is equal to u plus iv is analytic in a domain D, then u and v satisfy the Cauchy-Riemann equations, that is dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. So this is the necessary condition. Let us prove this one. Proof. Let f of z is equal to u of x comma y plus I into v of x comma y be analytic in a domain D. So it is given. So by definition of analytic, it is differentiable. So the derivative exists. Derivative of f of z, that is f dash of z is equal to limit of f of z plus delta z minus f of z divided by delta z, as delta z tends to 0 exists and it is unique. So now we have to substitute f of z plus delta z, f of z delta z in terms of x and y and also using u and v. So here we know that f of z is equal to u of x comma y plus I into v of x comma y and delta z is delta x plus I delta y, because z is x plus iy, delta z is delta x plus I delta y, and f of z plus delta z is u of x plus delta x comma y plus delta y plus I into v of x plus delta x comma y plus delta y. Next we have to substitute these things. F dash of z becomes limit delta z tends to 0 u of x plus delta x y plus delta y plus I into v of x plus delta x y plus delta y minus u of xy plus I into v of xy divided by delta x plus I delta y. So here we consider two cases. If delta z is purely real, So it is real, then imaginary part delta y is equal to 0. Therefore, delta z is equal to delta x. Then the limit f dash z is equal to limit of delta x tends to 0. So in this limit, we have u of x plus delta x comma y minus u of x comma y divided by delta x. So here change in x keeping y constant. So it is dou u by dou x. Similarly, in the second part, we take I as a common v of x plus delta x comma y minus v of x comma y divided by delta x. Here also the x variable changes keeping y variable as it is, keeping y constant. So it is a derivative of v with respect to x. So it is dou v by dou x. So this is f dash of z, call it as 1. So this is very important formula for the next unit, next topics, to solve some problems on analytic functions. Next part, so if the delta z is purely imaginary, first case we consider delta z is purely real. In second case, we consider f delta z is purely imaginary. It is imaginary, there is real part is equal to 0. Delta x is equal to 0 and delta z is I delta y. So only we have imaginary part. And substituting this, we get f dash of z is equal to limit delta y tends to 0. So here we have u of x comma y plus delta y minus u of x comma y, separating real and imaginary parts, I delta y plus I into v of x comma y plus delta y minus v of xy. Here x is constant, y changes, y is a changing. So here we have to find the derivative with respect to y keeping x constants. So this derivative is dou u by dou y. 1 by I is constant plus here I cancel, dou v by dou y. So this 1 by I becomes minus I if it comes to the numerator or by rationalizing. So call it as 2. Here f dash z is same. So the derivative is unique. Since the derivative is unique, 1 and 2 are equal. So by equating 1 and 2, from 1 and 2, equating the real parts and imaginary parts, we get dou u by dou x is equal to dou v by dou y, and dou v by dou x is equal to minus dou u by dou y, or dou u by dou y is minus dou u by dou x. These are called Cauchy-Riemann equations, and these are the necessary condition for a function to be analytic. So with these equations, we have to solve some problems on analytic functions. First example, verify whether the real and imaginary parts w is equal to sin z satisfy CR equations. So you have to verify CR equations, that is dou u by dou x is equal to dou u by dou y, and dou u by dou y is minus dou v by dou x. So let us find u and v. To verify CR equations, we have to find real part and imaginary parts u and v. So for that, we have to substitute z is equal to x plus iy. It is sin of a plus b, sin a cos b plus cos a sin b. So here we have cos of iy. So we know that cos of iy is cos hyperbolic y. So by using hyperbolic function and Euler's formula, cos iy is cos hyperbolic y. Similarly, sin iy is I sin hyperbolic y. Now it is in the form of u of x comma y plus I into v of x comma y. Here real part u is equal to sin x cos hyperbolic y, and imaginary part v is equal to cos x sin hyperbolic y. So next we have to find the partial derivatives with respect to x and y. So dou u by dou x is differentiation with respect to x, differentiation of sin x cos hyperbolic iy as it is. Differentiation of v with respect to x, differentiation of cos x minus sin x, keeping sin hyperbolic y as it is. Similarly, we find differentiation derivative, partial derivative with respect to y, dou u by dou y. So keep sin x as it is. Differentiation of cos hyperbolic, it is sin hyperbolic y, and differentiation of v with respect to y, dou v by dou y, cos x as it is. Differentiation of sin is cos hyperbolic y. So by comparing, by observing, we see that dou u by dou x is equal to dou v by dou y, cos x cos hyperbolic y cos x cos hyperbolic y, and dou u by dou y is negative of dou v by dou x, that is dou v by dou y is minus dou v by dou x. So these are CR equations. CR equations are satisfied, CR equations are true. So let us see one more example. Show that the derivative of f of z is equal to cos z exists using CR equations and find its derivative. So you have to find the derivative using CR equations. So again, to verify CR equations, to apply CR equations, we need to find u and v. So f of z is cos z, put z is equal to x plus iy, cos of a plus b, cos a cos b minus sin a sin b. Cos iy is cos hyperbolic y, sin iy is I sin hyperbolic y. So here we have u is equal to cos x cos hyperbolic y and v is equal to sin x sin hyperbolic y. So again, by differentiating partially with respect to x, we get dou u by dou x is equal to differentiation of cos x minus sin x cos hyperbolic y, differentiation of sin x cos x sin hyperbolic y. Similarly, dou u by dou y, differentiating with respect to y, so differentiation of y keeping x constant, cos x sin hyperbolic y, and dou v by dou y minus sin x cos hyperbolic y. So here we observe that dou u by dou x is equal to dou v by dou y, that is minus sin x cos hyperbolic y, and also dou u by dou y is negative of dou v by dou x. So CR equation satisfied. Next we have to find, using the CR equations, we have to find f dash of z. So we know that f dash of z is equal to dou u by dou x plus I into dou u by dou x. So substitute dou u by dou x, dou v by dou x. So dou v by dou x is minus sin x cos hyperbolic y plus I into minus cos x sin hyperbolic y. Taking minus as a common, we have sin x cos hyperbolic y plus I into cos x sin hyperbolic y. So here we write cos hyperbolic y as cos iy, I sin hyperbolic y as sin iy. It is in the form of sin a cos b plus cos a sin b. It is nothing but sin of a plus b, sin of x plus iy. So x plus iy is z, it is sin z minus sin z. So derivative of cos z is minus sin z. So third example, verify CR equations for f of z is equal to e to the power z. So it's a simple problem. So you can write z as x plus iy, e to the power x plus iy, a power x into a power iy. So by using Euler's formula, we write e power iy as cos y plus I sin y, e to the power x cos y plus I into e to the power x sin y. Here real part u is equal to e to the power x cos y, imaginary part is e to the power x sin y. So by using this, we can find the derivatives. We can find the derivatives. Dou u by dou x is e power x cos y, dou u by dou x is e power x sin y, dou u by dou y is differentiation with respect to y, cos y is minus sin y, so minus e power x sin y, with respect to y it is e power x sin y, cos y, differentiation of sin y is cos y. So comparing, we get dou u by dou x is equal to dou u by dou y, and dou u by dou y is minus dou v by dou x. CR equations satisfied, hence f of z is analytic by necessary condition. So example 4, show that f of z is equal to log z is analytic and hence find f dash of z is equal to 1 by z. Let f of z is equal to u plus iv. So here it is log z, log of x plus iy. We cannot expand log of x plus iy. So we transform logarithmic function into exponential function. So for that we take f of z is equal to u plus iy. So here also we have to find u and v. To verify it is analytic, we have to find u and v, and then we have to verify CR equations. So e plus iv is equal to log z to the base e. So by using exponential logarithmic transformation, e to the power u plus iv is equal to z. So again by applying Euler's formula, e power u into e power iv, that is e power iv is equal to cos v plus I sin v into is equal to x plus iy. Z is x plus iy. So equating real parts, we get x is equal to e power u cos v and y is equal to e power u sin v. Imaginary part, squaring and adding, we get x square plus y square is equal to e power 2u, because cos square plus sin square is 1, and 2u is equal to, again applying log, 2u is equal to log of x square plus y square, u is equal to 1 by 2 log of x square plus y square. Again by dividing y by x, we get tan v. So v is equal to tan inverse of y by x. This is imaginary part and this is real part. So after finding u and v, we have to find the partial derivatives with respect to x and y to verify Cauchy-Riemann equations. So dou u by dou x is x by x square plus y square, and dou u by dou y is y by x square plus y square. So just applying the properties of differentiation. Differentiation of log x is 1 by x into differentiation of x square plus y square. So after simplification, we get x by x square plus y square. Similarly, y by x square plus y square with respect to y. And dou y by dou x, it is tan inverse. So differentiation of tan inverse is 1 by 1 plus x square. So 1 by 1 plus y square by x square. So taking LCM, it becomes x square plus y square, and also the differentiation of y by x with respect to x, it is minus 1 by x square, minus y by x square. So x square cancel, we get minus y by x square plus y square. Similarly, dou v by dou y with respect to y, same formula. Differentiation of tan inverse x is 1 by 1 plus x square into differentiation of y by x with respect to y. So 1 by x constant with respect to y, it's 1 by x. So dou v by dou x is x by x square plus y square. So by comparison, here dou u by dou x is equal to dou v by dou y, and dou u by dou y is minus dou u by dou x. So CR equations satisfied. Hence f of z is analytic. Next we have to find the derivative using CR equations. So we know that f dash of z is dou u by dou x plus I into dou v by dou x. Substitute dou u by dou x and dou v by dou x, that is x by x square plus y square plus I into minus y by x square plus y square. So same denominator, x minus iy divided by x square plus y square. So x minus iy, in the denominator x square plus y square, we express this x square plus y square using I. So it is x square minus iy whole square, a square minus b square, that is a plus b into a minus b. X minus iy cancel, only we have 1 by x plus iy. So this is nothing but z, 1 by z. So derivative of log z is 1 by z. So these are very important problems. Thank you.